Good evening to everyone. This site is already in the evening, so good evening, and thanks to the organizing committee for giving me this chance to share my work with everyone. So our work is based on ethanol dehydrogenation over carbon-supported K-MoS nickel ion-based catalyst. So at the moment, we are still testing this catalyst. Am I clear, right? Open clear. No? Am I audible? Hello?
Yes, we can.
Oh, you can hear me. Okay. So as I was trying to say, my presentation will be based on ethanol dehydrogenation over carbon-supported K-MoS nickel ion molybdenum disulfide based catalyst. So we are testing this. The reason why we are testing this catalyst is because, okay, we'll explain that later on. So the outline will be a modern understanding of catalysis by transition metal sulfide, ethanol dehydrogenation, and then the effect of support. We have activated carbons and alumina-based support, and then we have the effect of active phase composition, and then the effect of promoter atom. So with regard to the modern understanding of catalysis by transition metal sulfide catalyst, we have three models that are proposed. We have the model of K-MoS or NMOS phase, and then we have the electronic model of promoting, and then we have the rim edge model. So comparing the two, we can start with this one. This one states that when we promote the catalyst, the electrons will be donated to molybdenum, and then when the electrons are transferred to molybdenum, this will weaken the MO and S bond, and then when we weaken that bond, the vacations will form. And then on the model of K-NMOS phase, it states that when we promote the TMS catalyst, the CMOS phase will form, which is considered as an active phase of this catalyst. And then under reaction conditions, we're going to lose sulfur in the form of hydrogen sulfide, and then when we lose sulfur, we're going to form those vacations where it improves the alters the catalytic activity. And then we have the rim edge model, and then the rim edge model states that if we can control the height and the diameter of our crystallites, so we can also alter the catalytic performance. We can alter the catalytic performance by controlling the height or the length of our crystallites. And then the second slide, this is our aim. So our aim, like we know, these catalysts are more used on hydrotreating. And then again, recently they have been used for several years, for many decades in syngas conversion. So what motivated our study is because when these catalysts are used, when syngas is converted, other studies, they convert CO by co-feeding CO with methanol or ethanol. And then they have found out that those intermediates, they can reabsorb on the surface of the catalyst, and then those intermediates can be converted to other products. So this is the case when ethanol is one of the products that is produced from syngas, and then again co-feeding ethanol and syngas, we're going to have an increased amount of ethanol and other products. So we are trying to study the the route of ethanol conversion over the same catalyst. And then the other interesting part is that we don't have much literature out there on direct ethanol conversion over TMS catalyst, which is one of the interesting things. So this is the basic catalytic preparation. So I think we don't have to go through it because it's very clear. And then here we tested the textural properties of our support. So the first part, we have support. We tested different support. We tested activated carbons, and then we tested alumina-based catalyst. We have CCA, carbon-coated alumina, and then we have alumina, carbon-coated alumina, and then we have two activated carbons, BAO and namely AG3 and BAO. And then as we can see, and then as expected, when we introduce our active metals, our surface area decreases, and then some of the pores, they are blocked, the pore volume reduces, and so forth. And then we explain this by some of those pores will be blocked by the active metals, and then they will be absorbed inside those active metals. And then another advantage is the comparison of the two. We have activated carbons and oxide supports. And then as we know that between the two, for us to improve our catalytic activity or catalytic performance, we have to try to reduce the interaction between the support and the active metals. And then in theory, we know that activated carbon, the interaction between active phase and the support when we are using activated carbons is lesser compared to alumina. So we expect that the two catalysts will be more active than alumina-based catalyst. And then here we have the pore diameter. And then as we can see, there's the huge difference between the pore diameter between the activated carbons and alumina-based catalyst. And then here we characterize our catalyst using TEM, high resolution TEM, and then we calculated the statistic analysis. And then the only difference that we noticed is between the dispersion of our molybdenum disulfide and then the average length of our crystallites. And then the average starting number ranges almost around the same amount. So our activated carbon-based catalysts, they had higher average length compared to those who are supported on oxide support. And then as the average length increases, and then we saw that the dispersion decreased. So it's expected because as these particles grow, so it means the dispersion will be lower. So when the length grows and then the dispersion becomes very low. Then here the metal distribution of CO of cobalt and molybdenum species represented on the surface of the sulfide K-MoS supported catalyst. And then as we can see here, the main difference will be between these three as shown here. And then again, the percentage of cobalt on the surface, we can see that again, the activated carbon supported catalysts, they have higher amount of this active phase. So this is considered as one of the active phase of this catalyst. And then this is classified as one of the inactive phase on the surface of TMS catalyst. And then we had the percentage to be higher under alumina-based catalyst. And then on the other hand, when we look at on the edges, these are the edges on the edges of our slabs, which plays an important role on the activity of the catalyst. So as the amount of the ratio on the edges increases, in a way, it should improve our catalytic performance. And then here we have the XPS results of our 4 catalysts. At the top, we have alumina. At the bottom, CCA. And then this side we have BAO and Ag3 or activated carbons. So the interesting part, we have almost the same, our diagram, they're almost the same, but the interesting part, we found catalyst supported on Ag3 to be different around this place. And then we explain this by intercalation of, after the addition of potassium into our catalyst, after the promotion with potassium, we assume that there was an intercalation. So potassium was placed between the labs. So those are the intercalation. And then those intercalation, when potassium is placed between the labs of molybdenum disulfide, it creates more active species or active centers, which is also can improve the catalytic activity. Hence, we found a difference in this catalyst Ag3. And then again, we assume that the conversion of ethanol, effect of support on ethanol conversion, we can support the theory, our argument based on this conversion, especially under helium, because under we used helium and hydrogen as our atmospheres for conversion of ethanol. And then as we notice here, even though BAO had better surface area compared to Ag3, but Ag3 was more active than BAO. And then that extra intercalation might explain why we had better activity under Ag3 as compared to BAO. And then this the product that we got from ethanol conversion. And then on the right, we have under the A is under helium atmosphere, and then B under hydrogen atmosphere. So the huge difference was seen under helium atmosphere, and then under hydrogen atmosphere, the catalysts were not that active. And then we assume that the catalysts lost their activity because of desulfurization, because we assume that during the reaction, hydrogen accelerate the formation of hydrogen sulfide. And as soon as we have that process taking place, so our catalyst loses its activity. And then the other thing, our major product was ethyl acetate. So we have ethyl acetate, we have acetaldehyde. So our main product was ethyl acetate. And then again, many reports have reported that under transition metal catalyst, ethyl acetate is the main product. So under both atmosphere, ethyl acetate was the main product. And then we saw a slightly, even though it's not yet conclusive, but we saw a slightly dependence of an increase of ethyl acetate with an increase of average length, and then a decrease of dispersion. And then here we tried to find a dependence of yields on catalytic acidity. And then it should be noted that we didn't find any correlation between total conversion with acidity. So there were no correlation between acidity and total conversion. But when it comes to a few of our main products, we saw that when the acidity of the catalyst increases, and then the amount of ethyl acetate decreases. And then when the acidity of our catalyst increases, and then the yields of acetaldehyde also increases. And here we represented the acidity. And then the interesting part is that when we look at the acidity of the support, especially for the activated carbons, we can realize that even though the support had lower acidity, but the catalyst, the acidity increased after the preparation, after the addition of our precursors. And we assume that the precursors, the solution of the precursors had more acidity than the support, hence the acidity increased. And then here, again, we compared, if we try to find the relationship between TOF and dispersion. And then we found a positive correlation whereby with higher TOF, we had lower dispersion. And then as the dispersion increases, the TOF decreases. And then we do explain this by the rim edge model. So when dispersion decreases, so it means the amount of our crystallites grow longer. So when they grow longer, that improves our catalytic activity. And then here again, we're trying to compare or to find correlation between the structural property of our catalyst and total product yields between liquid product, which is LP, and then hydrocarbons. And then when we look at the textural properties, we found out that our activated carbons had more microporous structures compared to mesoporous structures. And then the alumina-based catalyst had more mesoporous structure compared to microporous structure. And then those who had our activated carbons had more microporous, and then the activity increased with an increase in microporous. And then with a decrease, an increase in mesoporous, we noticed that our alumina-based catalyst had better activity when it comes to hydrocarbon synthesis. And then again, we compared activated carbons, powder activated carbons, and fiber activated carbons. So with the two, we're trying to compare which one is more active based on the fiber-based supports and then powder-based support. And then the powder, in terms of total activity, the conversion, the powder activated carbons were more active than the fiber-based support were more active than the powder-based catalyst. However, the high conversion contributes more to hydrocarbons, whereas under powder-based support contributes more to liquid products. And then we assume that for us to have a better activity in terms of liquid product production, we need the textural properties, those pores, microstructure, and then the volume of our pores. And then we explain again the activity. We explain this activity in terms, especially in terms of liquid products on the structural, on the crystallites. We can see that powder-based catalysts were characterized with higher crystallites compared to fiber-based catalysts. Even though we did it for these four catalysts, we didn't do the quantitative analysis to measure the length and the stacking number, but judging from a naked eye, we realized that these two had higher amount of crystallites compared to fiber activated carbons. And then these are product distribution. And then DAS was more active as compared to the previous catalyst. Ethyl acetate is still our main product. And then the fiber-based catalyst produced more hydrocarbons. So even this one, powder-based catalysts are still better supports for production of ethyl acetate and liquids product. And then again, we noticed that again, when it comes to alcohol, butanol 1 and then propanol 1, the powder-based catalysts were more effective compared to fiber-based catalysts. And the second part is about the effect of the active phase composition. And then we tested 4 catalysts supported on Ag3, activated carbon Ag3. We tested MoS, and then COMOS, KMOS, and then KCOMOS. And then, surprisingly, after the preparation of our catalyst, we saw a high decrease in surface area under COMOS, which is very unusual. And then we assume that maybe more during the preparation, the oxide precursors were still on the pores of the catalyst. Hence, we saw a huge drop in the surface area and then the pore volumes. And then, with the same catalyst, we tried to find the dependence of conversion on active phase composition, and then we didn't find a correlation between the acidity of the catalyst and the total conversion, as we can see on the right. So there was no direct correlation between conversion and acidity. So again, here we can conclude that our active compounds, they play an important role on the activity of this catalyst. And then this is our conversion. The conversion, we tested the conversion in 3 different loadings, but the main idea was to check the effect of catalytic composition. So as we know that, as expected, with the increase in the loading, we noticed an increase in conversion, which is expected. And then again, after promoting or modifying this with, let's compare the two. After modifying this catalyst with potassium, we saw a huge decrease in conversion. We saw a huge decrease in conversion. And then this might be explained by, we explain this by Fermi energy. The Fermi energy, whereby it says we had, when we promote or we modify molybdenum disulfide supported on Ag3, we saw a huge decrease in activity. And then this can be explained by decreased availability, because when we modify this catalyst, so we are decreasing the availability of MoS, and then that MoS, molybdenum disulfide, is the responsible site for activating hydrogen. So if we introduce potassium, we are reducing the site responsible for hydrogenation, which decreases our catalytic activity. And then again, the same thing was observed when we compare the two, because here we have KCOMOS, and then we have COMOS, and then here we have KCOMOS. And then when you compare the two, the same thing was observed. When we add potassium into this, we saw a decrease in conversion. And then again, this was explained by, we can explain this by Fermi energy again. And then the difference in conversion, a reduction in the availability of MoS sites involved in hydrogenation caused the decrease in activity comparing the two. And then interaction of K with the support and K with more also has an effect on decreasing the activity. And then again, the agglomeration and the pore blockage by the active species limit the deposition of active species inside the pores. So as the pores closes or they are blocked, so it means we're not going to have enough active phase on the support to improve on the surface to improve the catalytic activity. And then this is what we explained before about the rim edge model. And then in terms of our product distribution, again, ethyl acetate under all catalytic composition, the active phase composition, ethyl acetate is still the main product. However, after adding K, potassium, we can see that after adding potassium, there was a decrease in our product yield. And then interesting part, which is a good one for our study, is that after adding K, we realized that the amount of hydrocarbons decreased, and then a slightly increase in higher alcohols, especially under K commas. We saw a slightly increase in propanol 1 and then butanol 1, whereby here the amount of the two were almost negligible. And then here we're focusing on the effect of alkali metal addition to the activity of molybdenum disulfide catalyst. And then as we can see, adding introduction of potassium to our catalyst increases the stacking number of the stacking number of crystallites. And then when we increase this, decreases hydrocarbons and then increases the amount of alcohols. Decrease hydrocarbons and then increase the amount of alcohols, which is the same thing that we noticed. Here we don't have potassium, and then with the introduction of potassium to the catalyst, we saw a decrease in hydrocarbons. And then again, we saw a slightly increase in higher alcohols. We see the increase in higher alcohol, especially butanol and propanol 1 after the addition of potassium. And then the last part, even though we are still working on this one, we're testing the effect of promoter atom. We used cobalt, nickel, and then iron. And then both of them were supported under activated carbon and aluminum. And then again here we can see that activated carbons are still better catalyst compared to alumina. As the conversion increases, we compare this and this under both the same promoter atom, the activated carbons are still better supports. And then this is still under our current study. And then the short conclusion we can make from this: activated carbons are still a better catalyst. When to produce ethyl acetate, the better catalyst was the one that was promoted with cobalt, and then ethyl acetate, cobalt also, because the ethyl acetoacetate depends on the amount of ethyl acetate produced, because we assume that this produces forms through clean cell condensation. And then acetaldehyde, almost the opposite of ethyl acetate. So with an increase of ethyl acetate, and then we notice the decrease of acetaldehyde. And then for butanol, nickel was better. Nickel containing catalyst was better for production of butanol. And then for production of propanol, cobalt-based catalysts were found to be better. And then this is just the short conclusion. Alumina-based catalyst, mesoporous, lower conversion, decrease in average length of crystallites, and the TOF is low, but increased dispersion, and then higher favors hydrocarbon synthesis, and then ethyl acetate, and then activated carbon-based catalysts, which are microporous, they contain more microporous structure, and then higher conversion, increased average length of crystallites, favor high alcohol synthesis and ethyl acetate, and then the TOF is higher, and then decreased dispersion, decreased hydrocarbons synthesis, and decreased ethyl acetaldehyde. And then in terms of promoter atoms, when we introduce the metal potassium, favors higher alcohol synthesis, even though it decreases the conversion, but it favors high alcohol synthesis, and then decreases production of hydrocarbons. And then nickel favors butanol synthesis, and then again increases ethyl acetate synthesis, favors butanol 1. And then cobalt also favors ethyl acetoacetate synthesis, favors ethyl acetate, and then propanol 1. And then this one was found to be less active, whereby we saw lower yield over this catalyst. And then the conclusion is the same as the one that we mentioned above. And then this is our products after our experiment. And then many reports have said the perspective of using the oxygenates from ethanol conversion. The result mixture of oxygenates contain mostly ethyl acetate and derivatives of high alcohols, which are widely used as high performance solvent in paint industry, as well as high value octane number gasoline. So these products the products of ethanol conversion can be beneficial because they can be used as solvents and additives on gasoline. So those are some of the conclusions that we made. And then thank you for your attention.